this would be maybe a cataract or say a non-complete optic atrophy. So you've got pallor of the disc, but it's not complete, so there's still vision. So you got your this is your norm. This is your hill of vision. That's your normal hill of vision for that age-matched hill of vision. And say your patient then would have this, because they've got a nuclear sclerotic cataract. It's just uniform. You're just absorbing light, creating diffraction. You're just not as sensitive. Or you have disc pallor. So all that transmission has been reduced across the board, all frequencies, the whole field. Okay. So what would happen here is your total deviation plot, which is that first one. All that does is all that does is compare stats, right? Normal to abnormal. And so you basically get loss. Instead of that half hemifield, you get the whole thing lost there. So what the pattern deviation does is it calculates a mu, and this would be patient. So this would be patient. It calculates the mean sensitivity across the field. So for this patient, it's the same. For this nuclear sclerotic cataract or incomplete optic atrophy, it's the same because it's uniform. The mean sensitivities are already the same. And then it just subtracts the SAP. So you minus that new thing out of there. And what you're left with is this, which is the original age-matched norm. And so what happens is your pattern deviation, can you see that? Is that visual angle okay to see this? No? No? Sorry. It says B.
What? Can we pull that up?
Well, I'm going to have to use this. Let me just make it smaller. Is that smaller? Is that enough? Yeah. So that's just 0. So your pattern deviation, and this highlights the first step of what Kelly was saying. If it's different, something's going on. Well, the pattern deviation would be clear now. So it's blank.
Dr. Wong, that new hill of vision looks the same as the old hill of vision.
This?
Yes.
Yes, because it's a uniform sclerotic cataract, or it's an optic nerve that is completely across the field, same sensitivity. It's purposely done that. So you have an example here. Always better by example, right? It's key D. Pattern deviation.
T is what? Total.
Total deviation.
Well, is the third hill of vision you drew supposed to be smaller than the other two, or supposed to be the same?
This is the same. This is just your. All you're left is with like the norm. Okay.
So the pattern deviation just compares the patient to the normal value?
Okay, so what the pattern deviation does is it calculates the mean sensitivity and then just gets rid of it, and then it runs through that comparison of stats again.
Okay.
So you could write actually. So here, this would be versus stats, right? Versus norms, age-matched norms. And then the same thing would happen here. Versus See, pattern deviation does this same step, it just has this one step in between. It calculates a new patient mean.
Can you just maybe do that one more time?
Yeah, that would be
I
up
really
written
have no
down.
idea what you just did.
Well, number one now. All of this to go.
Oh, no.
Can you
So okay. So you've got this solid line, which is your age-matched norm hill of vision. Whatever age you are, 25, 40, 80, you're going to have stats for, this is what I'm comparing the field to. This is the patient's actual hill of vision, calculated from these raw scores here. So this is from the numeric raw scores, the decibel values. Then there's just this comparison of norms. It's just versus age, and that's how you get the total deviation. And you'll get dark. You'll get loss. It's worse than the age-matched norm.
But
Dark
the-
is bad.
the line? Is that saying that it's blacked out? Those lines, or you're saying there's an area?
Yeah, it's just a relative, like, if it's clear, it's white. If it's dark, you have loss.
Okay.
But this one's saying that it's the
The whole-
loss
yeah,
is
that's what I'm-
even across the entire.
Because it's a full cataract.
Okay.
Okay.
All right.
And then what the pattern deviation is, it has this other step before it does the same thing. So this step and this step is the same, but before that, it actually subtracts out the patient's hill of vision, which in this case is the same because it's a uniform. There's no recalculation needed, it's just equal loss across the field. So it just takes this away. And so visually, this curve should be the same as that. I just crunched it up because the angle was bad. This should be the same. And so now if you do that, you have zero difference, so you have a clear field, pattern deviation. So this means, this is your classic thing you're gonna see with a cataract. If you get a field where total deviation, oh, I got a lot of loss, and then pattern deviation is clear, oh, that person just has either a uniform cataract, most common case, or they might have something like this. And again, Bechamel by example. So in slide 47, next slide, here you go. So in a cataract, you're going to have reduced absolute values. Now here's the point again. You're a tech. You're a doc this summer. You look at this thing and you go, that doesn't look that bad. It's not all white, but something's going on maybe. You look at these numbers, you got 20s. So again, the higher the decibel number, the better the patient is in sensitivity. You look down here and you got this massive loss compared to age, but then here you got nothing. Okay? So what does this mean? This means exactly that. It means that the machine calculated the patient's field of vision, took that away, and then compared again, and you get nothing. So this is basically your classic case of my lesion for this patient is just some general cataract or maybe optic nerve. You'll look and see